Swayam Prabha. Digital India. Educated India.
Welcome students, we meet once again for a lecture on stress distribution in soils. We have come a long way in the last two lectures. We now have a fairly good idea about what this problem of stress distribution is all about. In the first lecture, we had seen the importance of this problem, where this problem is arising, where we need stress distribution in soils, where we are particularly concerned about the ability of the foundation to withstand the stresses from the superstructure without distress. Under all these circumstances, we need a method to compute these stresses. So, in the last lecture in particular, we were trying to take a look at the methods that are being used for computing stresses. So, let us take a look at one of the slides. This slide summarizes briefly what we discussed in the last lecture. Let us read it. We saw in the last lecture particularly what is the method for computing stresses, which is based on the theory of elasticity. If you remember, I mentioned that there are major contributions based on the theory of elasticity to the subject of stress distribution from scientists such as J. Businesq, who gave a theory for computing stresses based on theory of elasticity, rather a method for computing stresses based on the theory of elasticity. This was followed in the year 1938, almost 40 years later, by Westergaard, who extended the method of Businesq to circular areas. Then came in 1942 a contribution from Newmark for computing stresses beneath any arbitrary area. Then we also saw in the last lecture how to compute these stresses due to a concentrated load. We saw in fact two broad approaches, one which I called the approximate method and another the so called Businesq solution. If you recollect, in the approximate method we just assumed that soil is a particulate material. The stress from the foundation gets transmitted to the soil through the grains, and in that process it disperses. If this is the foundation, we saw that the soil distributes the stress, and at any depth z, the area over which the stress gets distributed is no longer length into breadth, but it is length plus depth into breadth plus depth. And so, if there is a load P here, it gets uniformly distributed over this area of L plus Z into B plus Z. Now, this is an approximate method because the actual line which represents the boundaries of the area of distribution is approximate. Now, on the other hand, the Businesq solution takes a different approach. It's based on theory of elasticity. Now, let us see in this lecture, today's lecture, how to use Businesq's approach for computing stress distribution due to first a point load and then due to a line load. Let us briefly recapitulate what theory of elasticity is all about. It is necessary, although we have covered it in the last lecture, to briefly go through this so that we will be able to appreciate Bushnell's theory a little better. If you see this slide, we started with the assumption that soil is a semi-infinite medium or half space. It is a continuum, meaning there is no break, although the medium is consisting of granular material with distinct boundaries between the grains. We assume this to be a continuum. Next, we assume the medium to be homogeneous. The advantage is every element of the medium is similar to any other element. If we understand the behavior of one element, then we can extrapolate it to all the other elements and hence to the entire half space. That is the idea of assuming homogeneity. It considerably simplifies the problem. In nature, of course, it may be difficult to find perfectly homogeneous material. We will see later on how best non-homogeneity or inhomogeneity can be included. We also assume that the soil has equal properties in all directions, that is isotropic. Most importantly, we assumed that the soil has no weight, which meant that there were no initial stresses and there was no initial deformation. The idea is that we will be in a position to calculate the stress in the medium purely due to the applied stress due to a foundation. The self weight of the material of the soil, which contributes a stress by itself, can always be computed if we know the depth and if we know the unit weight of the soil, and therefore, theory of elasticity need not be used for computing the stress due to the weight. Then modulus of elasticity is assumed to be constant, so also Poisson's ratio and other elastic constants. And then lastly, principle of superposition is valid. That means, if for example, more than one load is applied to the foundation, the stress due to each load is added to the stress due to the next load, and therefore, we apply the principle of superposition. In all this, we have made an assumption also that the foundation is perfectly flexible, so that the contact pressure at the interface between the foundation and the soil is uniform. Now, all these assumptions and their importance has been laid out very clearly both in the last lecture, and I have emphasized it again this time. Now, are they really applicable? A question automatically arises in the mind. Are we oversimplifying the problem? Are we justified in making these assumptions? Are they really acceptable? Well, to some extent they are acceptable. To a great extent, application of this theory in practice has vindicated our stand that it is reasonable to assume the soil to be homogeneous, isotropic and a continuum, and also elastic in nature. You can say that the validity of the method, validity of these assumptions used in the method of computing stresses has been borne out by trials in the field, and therefore, we can justifiably say that the method can be used with reasonable confidence in practice. However, it must be noted that there can be deviations from the conditions which have been assumed. If there are deviations, we shall have some approximate way of accounting for those deviations using as a basis the expressions which we will be deriving on the basis of these assumptions. That is, we will derive a set of conditions, a set of equations or expressions for these ideal situation, and any deviation from this will be accounted for in some empirical way. Let us take a look at the next slide. This shows the soil element and the coordinate system. This we have seen already in the last lecture too. So, this is the element which we shall be analyzing to find out what is the stress in the element, and this is the coordinate system that we shall be using, and this is the load P, which is known as the point or the concentrated load, due to which we are interested in finding out what the stress at point P is. We were taking a look at the fundamentals of the theory of elasticity yesterday. The theory of elasticity assumes 4 or 5 major tenets. Number 1, it says that the material is in equilibrium. A typical element inside the soil is in equilibrium under the action of the stresses which are acting on it. Now, this is an essential condition and a justifiable condition, because in practice we want safety. We want the element to be in equilibrium, therefore, the foundation will be in equilibrium and hence the superstructure. Therefore, it is a perfectly valid, justifiable requirement to state that equilibrium must be satisfied by the element for the set of forces or stresses which will be acting on it. Now, we have seen in one of the diagrams earlier that every surface of this parallelepiped is subjected to one normal stress and two shear stresses. Now, if we calculate the forces on each one of these planes and write down the well known equations of equilibrium for sigma x equal to 0, sigma y equal to 0 and sigma z equal to 0, this is what we will get. You can see here I have written three equations. One of them says sigma fx equal to 0, and you find that it has a term which is nothing but the rate of change of sigma x in the x direction, then the rate of change of shear stress tau xy in the y direction, rate of change of shear stress xz in the z direction, plus a so called body force x in the x direction. This is a force which is force per unit volume, which I mentioned yesterday. Now, if we write equations for Fy equal to 0 and sigma Fz equal to 0, we will get similar equations. All these three together constitute the so called equilibrium equations of a typical three-dimensional problem of stress distribution. In this, if Z is the vertical direction, Z in fact represents the force in the vertical direction per unit volume of the soil, which means that it is nothing but the weight per unit volume of the soil, that is, it is nothing but gamma of the soil. Now, we have just made an assumption that gamma or the medium weight does not exist. The medium is weightless, and which means therefore that we are ignoring the body stresses. We will also be ignoring the stress x, we will also be ignoring the stress y. That means, we shall be ignoring all these body stresses, and then the equations of equilibrium will simplify to merely rate of change of stresses sigma x, sigma y, tau xy, sigma z and so on. Now, you will see here that there are 3 normal stresses, 6 shear stresses, but moment equilibrium equations, if we write and solve, we will find that tau xy is same as tau yx, tau xz is same as tau zx. We will also find that tau yz is same as tau zy, which means that effectively we will be having 3 normal stresses and 3 shear stresses which are unknowns. We have 3 equations, but we have 6 stresses which are unknowns. So, 6 unknowns, 3 equations. Obviously, equilibrium condition alone will not help us to calculate stress distribution, because we have lesser number of equations and greater number of unknown stresses. Therefore, we need to make, or we need to consider some other condition as well, and that is why we went yesterday also to the second condition, if you see this slide, which is the strain displacement relations. What are these strain displacement relations? I had explained yesterday again that if any typical surface of the parallelepiped is considered, it elongates as well as distorts. So, there will be normal strains as well as shear strains. So, in a parallelepiped, on every surface there will be 2 normal strains and 1 shear strain, and therefore, in all, in a 3-dimensional problem, we will have normal strains epsilon x, normal strain epsilon y, normal strain epsilon z, and also distortion or shear strains, which are nothing but variation or deviation in the angle where the original value of the angle was 90 degrees. So, the change in angle of an original 90 degree angle is what is known as shear strain. It can be shown from geometry that the shear strain will be equal to this in the xy plane, in the yz plane this, and zx plane this. Now, you will find on the right hand side of all these equations there are notations such as U, V, W. These are nothing but displacements. So, effectively now we have strains and the displacements related to each other. After all, strain is nothing but displacement by original length or change in length by original length, and therefore, strain displacement relationships can be expressed as epsilon as a function of U or V or W, and that is what we have. Now, if you see this, once again we have 6 equations and how many unknowns are there? There are of course 6 strain components, but the displacements are also unknowns, and therefore, we have 9 unknowns. So, we have 3 plus 6 9 equations, we have 6 plus 9 15 unknowns. Obviously, we are therefore not yet ready to solve this problem completely to obtain the stresses. Not only that, in the second set of equations which we have written down, there are no stresses. That means, there are additional unknowns coming into the picture in the form of strains and displacements. Actually, therefore, these 15 are the unknowns of this problem. It is not only the stresses, but the strains and the displacements are also unknowns. Primarily, of course, in this chapter which we are discussing, we are interested in the stresses, and therefore, our basic unknowns are the stresses. However, we need to solve all these equations in order to arrive at finally the stress values. There are obviously inadequate number of equations compared to the number of unknowns. Therefore, we need to look for some additional conditions, but without increasing the number of unknowns, and that is what really theory of elasticity does for us. Let us see the next transparency. Take a look at this. Here I have written down the stress strain relationships. Actually, in the previous 2 sets of equations, really there was no theory of elasticity coming into picture. It was all equations pertaining to the equilibrium or the deformation of a typical element in the medium in a continuum. Theory of elasticity really enters the picture now. Now, if you see, the first equation is nothing but strain on the left hand side, modulus of elasticity and all the stresses on the right hand side. Poisson's ratio also is included. This equation is extremely simple to understand and derive. Any strain in any direction, we know according to theory of elasticity, must be equal to the stress divided by the modulus of elasticity. I am simply assuming that stress is linearly proportional to strain, or in other words, sigma is equal to some constant which I am calling as the modulus of elasticity into the strain. Now, if you see this, epsilon x is the strain in the x direction. It must be therefore obviously getting a component from the normal stress sigma x, which is also in the same direction as epsilon x. So, the component contributing to normal strain in the epsilon x in the x direction will be sigma x upon E. But when we are dealing with an element, if sigma x is contributing to a stress or a strain epsilon x, due to Poisson effect, due to the Poisson's ratio of the material, this material, if it undergoes compression, it will undergo in the vertical direction, it will undergo elongation in the lateral or horizontal direction, which means that this is also going to affect the strain in the horizontal direction. If this stress sigma x is affecting the strain in the x direction, due to Poisson effect, it will also affect the strain in the y direction. Now, conversely, the stress in the y direction will affect the strain in the x direction through the Poisson's ratio, and that is what we have written here. We have seen that if there is a compression in the vertical direction here, there is an elongation in the horizontal direction. Similarly, therefore, here if sigma x upon E is a positive contribution to epsilon x, the contribution from sigma y through Poisson's ratio